Okay, thank you, Patrick. And Patrick, can you confirm that you can see the slides?
I can see it, yeah.
All right, great. We gotta let some more people in here. Okay. All right. So at this point in time, epidemics are now a lived experience for all of us. And so to motivate this talk, by way of background, I want to talk about why we model epidemics. Here we go. So why do we model epidemics? And this graphic that I've shown here is this classic flattening the curve graphic that circulated in the early stages of the pandemic last year. And so it may be a bit nostalgic in some senses at this point. But what it does illustrate is this idea of the value of projections, the value of making predictions using models. So both of these curves here are projections into the future. The red curve represents the number of cases that we would have without protective measures, and the blue curve is what we get with protective measures. And we can see that the protective measures allow us to avoid overwhelming the capacity of the healthcare system. So the ability to make predictions and have models is useful because it lets us know what's coming, and it gives us an opportunity to optimize an intervention strategy that gives us a better outcome. Okay. One point that I want to make at this time is that an epidemic model is only as useful as it is both detailed and accurate. If you have flaws in your epidemic model, then there are going to be flaws or limitations on the kinds of predictions and optimizations and intervention strategies that it's suitable for testing. Okay, so given that, how is a useful epidemic model built or structured? Well, if you want to model an epidemic occurring in the United Kingdom, it is not simply enough to have a model that treats the UK as some monolithic population block. And that if you know the number of cases, then that's all you need to know. I mean, that's the figures that we often look up that are reported. You know, what is the total number of cases of coronavirus this past week? But that's not enough to build a model. You need a fine-grained resolution of geographic detail. You need to know where people are getting sick, and you need to know where those people are traveling as well, because that travel is a way that disease is spread. Okay, but even that is not enough on itself. You need, on top of that, you need a foundation of the model, which is the individual disease dynamics. And in this talk, I'm breaking that down into a description of transmission, progression of the disease, and recovery. Okay, so this foundation stage, the individual disease dynamics and modeling of that, is what I'm going to focus on in this talk. Okay, one thing to note is that the level of detail and the complexity that's put in at this foundation level is carried and transferred up to all of the higher levels of resolution and structure of the epidemic model. And so if you're going to test and optimize intervention schemes, that creates a pressure to have the simplest possible model at the foundation level, because you're going to carry that complexity through to all the higher levels. And so for practical calculations, you want a sufficiently simple or workable model at this level. But at the same time, every time you accept a compromise in accuracy or detail at this level, it means that your epidemic model is ultimately less useful for making predictions by the time it gets to the, full scale level of resolution. Okay, so we're going to start this talk by looking at a classic and popular model of disease progression, model of an epidemic, and that is the basic SIR model. So the basic SIR model is not often used in real epidemic modeling applications because of its limitations, but it's a nice place to start to understand the kinds of models that are used. Okay, so in an SIR model, the entire population is broken down into three compartments. You have those that are susceptible to infection, you have those that are presently infected, and you have those that are recovered from the disease. Now, the limitation of this model comes in this infected compartment. And it's that this infected compartment, everyone in the infected compartment is treated as being entirely equal. It's just a homogeneous block of infected people. There's no memory to the infected compartment. So that means that, for example, when somebody is infected, in reality, there's a latent period of about 5 days where they can't infect another person. Well, the SIR model doesn't have that. Another limitation in the similar vein is that in reality, somebody gets sick, and then it might be 15 days later that they would go to the hospital. Okay, that time lag, that memory, is going to be absent from the SIR model. In exchange, though, you get a very simple mathematical structure to the model. It's just this ODE model with different rates for moving between the compartments. And you can tune an average time for transmitting the disease, and you can tune an average time for recovery from the disease. But that's as fine as you can tune the dynamics of this model, and that presents limitations. Okay, so if you want to overcome those limitations, the first and perhaps simplest thing that you could do is to just extend this from one infected compartment to multiple infected compartments. And what that allows you to do is, for example, if you wanted to have that latent period at the beginning where you can be infected but not able to transmit the disease, you could say, for example, that in this first infected compartment, none of the infected people are infectious. So these betas now represent the rate constant for transmitting the disease in each of these compartments. You can tune those betas so that in the early stages it's low, and then in middle stages it rises, and then in later stages it falls again. Okay, so adding more compartments is a way of giving yourself more resolution of the disease progression and of the transmission dynamics and of the recovery dynamics as well, because you can have people recovering from each of these different stages. So you can tune the distribution of recovery times. The disadvantage is that every compartment that you add gives you more complexity to the model. You have to decide what those parameters are going to be in there, and it makes it more difficult to solve because you have more compartments to solve at every time step. Okay. So, but here's the question that naturally arises, though. What does one get in the limit of n going to infinity? Now, clearly, you would never do calculations with this model with n going to infinity, but just as a thought experiment, what happens is that it converges to something that that is continuous, basically. The discrete stages are replaced by a continuous coordinate of time since infection. So rather than moving from stage 1 to stage 2 to stage 3, your infection continuously ages from 0 days since infection to 1 day since infection, and so on. So if the discrete problem is being replaced by a continuous problem, does there exist a more efficient discretization of the same continuum limit that would give us all of the advantages of having all of these additional compartments with none of the costs of having a high number of compartments? Can we do the same thing with fewer compartments if we structure their interactions differently? Okay, that's essentially the question that this boils down to. So in the next few slides here, I want to walk through what a time since infection model looks like, how it sort of reframes from the compartment perspective to the continuum perspective when you start thinking about time since infection. Okay, so once you've got time since infection, instead of having different transmission rates, different betas for each compartment, what you have is a value of beta, a transmission rate, that varies continuously with the time since infection, or the age of the infection. Early on, you have this incubation period, then over time you start coughing a little bit, then you start coughing a lot, and then you start coughing less, and you're less infective, you're on your road to recovery, right? And so this is just a continuous curve replacing all of these discrete values of beta in the different compartments. The next thing to look at is, instead of having a population of infected persons in each one of these individual compartments, you have a density of infections with age tau at a given time t. So this curve here, I of t and tau, density of infections with age tau, what this does is this essentially plays out the entire history of the epidemic in reverse. So if you had a first wave of the disease and then rising cases at some time later, what you would see is that old infections dating to the first wave have a high time since infection, and then the newer cases have a lower time since infection, and a negative slope on this curve represents rising cases, for example. Okay? So, and then moving forward in time, basically what's going to happen is this whole curve contains the whole history of the epidemic, and as time moves forward, so does this curve, right? This curve marches forward in tau as the system marches forward in time, right? It's just preserving the history of infections. Okay, the last thing is the recovery dynamics. And here we've done things a little bit differently, not just from compartment models, but also from the way that other time since infection models tend to do things. So usually what's done is you define a rate constant for recovery out of the infected population at every age of infection tau, right? The trouble with that, and is even easily seen from the compartment models, is that your recovery rates are coupled to the transmission rates. You can't decouple the two when you do that, because if I move people out of the infected class at stage 2, then there are fewer infected people at stage 3 to participate in transmission. So I can't independently tune my beta of tau and my gamma of tau, for example, for recovery dynamics. Okay. If you want to decouple those two, it can be done. And the way that it can be done, I think, is quite simple and, in my view, more easily parameterized from the available data that one might collect on cases. All you need to do is look at the recovery probability, phi r, as a function of the time since infection, or the age of the infection. So when someone is initially infected, early on, there's a latent period where you can't have recovered yet. The disease hasn't had a time to grow, okay? And then after some time, people who have mild cases will recover early on, and people who have more severe cases will recover at a later time, right? And if you know the proportion of recovered persons at every time since infection, and going back to the previous slide, you know the whole history of infections, the age of every infection that there is, then you can figure out what the recovered population is at any time. And you can also do this for other classifications, not just recovered. You can break down the population into as many different kinds of blocks as you like and repeat this same calculation when you want to know, for example, how many people are in the hospital. So just to interpret this graph here briefly, what it's showing is that if you take a particular time since infection and you do a vertical slice, the relative widths of each slice tell you how many people are in each of those compartments. Okay? And I think that this is how case data would probably be collected, not in terms of rate constants, moving from one classification scheme to another, but in terms of just numbers of how many people are in the hospital based on when they first started showing symptoms. Somebody checks into the hospital 3 days, 5 days after they started showing symptoms. Somebody moves to the ICU 6 days after they started showing symptoms. That's how I think the data is more likely to be parameterized than in terms of rate constants, which would have to be inferred from the data. Okay, so now that I've sort of framed how a time since infection model is set up and how a compartment model, which we're calling SIKR, since there might be K stages to the infected class, I would just want to show the equations side by side. There are similarities between the two, but what I want to focus on, is just the transmission one at this point in time. So we see in the transmission one for the TSI model, what you're doing is you're taking an integral over all time since infection within the infectious range. So we're going to say that there's some time t after which people are not infectious. So you're taking this integral over the infectious range, and you're figuring out how infectious people are at a given age of infection and how many people there are in that age of infection. You're just integrating over that group to figure out the rate at which infections are presently occurring. And in the compartment model, we see that that integral is replaced by a sum. And essentially, what this represents is a Riemann sum approximation of the integral. This is starting to tell us what kind of a discretization of the continuous problem we're actually working with. So in the compartment model, as I said, we're working with a Riemann sum approximation, and that's illustrated here. The accuracy of a Riemann sum approximation is order delta tau. So the spacing in time since infection that your individual compartments represent sets the accuracy of your model. Okay, this is about as bad of accuracy as a stable and converging numerical scheme can be. So this is showing us that there are opportunities for improvement on what the classical compartment model structure of an epidemic model might give. So let's explore what some of those improvements look like. Some of them are known, and one of them that we'll show we believe is new. Okay, so if you start from a Riemann sum, the first thing that you might think is to go to a trapezoid integration. So rather than having all of these overhangs and underhangs of rectangles, you move to trapezoids that much more closely approximate the shape of the curve. And so your accuracy now is not order delta tau, but it is instead order delta tau squared. And that's just for the transmission dynamics, though. If you want to have the whole model have accuracy delta tau squared, then you have to make sure that that same accuracy is preserved in your progression and in your recovery dynamics. Okay, the tricky one is the disease progression. So this is the advection equation, basically. Remember I said that in time, this curve essentially just marches forward. So it's being advected in time since infection by the passage of time. So that's what this equation looks like. So if you want to evolve this curve forward in time, you have to be able to numerically evaluate what its derivatives in tau are, for example. If you want second order accuracy, the first thing that you might think of would be to do a central finite difference approximation. Okay, that's good. It does give you second order accuracy if you are sure that the calculations are remaining numerically stable. There's a stability criterion that is quite stringent. Your time step that you're allowed to take goes as the square of your increment in time since infection. And that's quite restrictive, actually, especially if you want to have a lot of different stages for good resolution of the disease dynamics. Okay, so suffice it to say, that's not very good. We think we can do better. So how can we do better? Well, the first thing is that this advection equation is simple enough to be integrated to a form that looks like this. And this basically just says that the shape of the curve is preserved over time, and it's just marched forward in tau as time passes. And if we make our time step equal to delta tau, then we can exactly preserve this property. All you have to do is just march each one of these points to the same spot that the next data point was previously at, right? You just have to make sure that all of your points are uniformly spaced. You can't do some kind of adaptive spacing where you have more resolution at a certain age of infection, less resolution at others. Now you're restricted that you have to have uniform spacing of these points in tau. Okay, so if all of these points are being marched forwards, what happens with this first point over here? Well, it turns out that if you use a predictor corrector method to fill in what that first point is supposed to be, then you can get order delta tau squared accuracy at every level in this model. That's a fantastic improvement over the compartment models. A natural question might be whether you can move forward to do, for example, let's go back a slide, in this step here, what if instead of trapezoid rule, you did a Simpson's rule or something, so you could have fourth order accuracy? in your quadrature here. Could you do the same thing and use, for example, a Runge-Kutta method in order to have fourth order accuracy at this point here? And it turns out you can't. The reason that you can't do it, or at least that it's not easy or obvious how you would do it, is that you can't do fractional time steps with this advection scheme. The way we've done this advection scheme is we've exactly integrated the equation and cleverly taken a time step exactly equal to delta tau, and the accuracy that we've baked in here completely fails if we have to take fractional time steps, as would be needed for something like RK4. So this method is fast, it's pretty accurate, it's pretty efficient, but it's restrictive. You have to have these points evenly spaced. You have to take fixed time steps. You can't do adaptive time stepping, and the accuracy is never going to get better than delta tau squared. This method is known, it's used in various places in the literature, but what I want to talk about is a method that overcomes those limitations. So it gives you better accuracy, it gives you the opportunity to use fewer grid points, and it lets you do adaptive time stepping. So to achieve those things, to achieve those things, we're going to look for a Glurkin approximation. And what a Glurkin approximation does is it says, first of all, we don't need to worry about the whole history of the infection. All we need to worry about is those infections that are presently within this transmittable range. We don't need to worry about infections that were 6 months ago. Let's just make sure that we're modeling correctly the infections that are less than 3 weeks old, for example. So those are the ones that are still spreading, okay? Then within that infectious range, you model this curve. Oh, this should just be I of t in tau, not the beta should not be there. This is just the number of infected people. You model that portion of the curve via a polynomial fit, right? And so you have these polynomials in tau, and you have the coefficients that evolve forward in time t. And what that lets you do is fit the curve with something like that. Now, this curve is going to be terrible at tau larger than t, but the idea is that it's set up to fit this curve properly in a limited window. And if you do this, and if it works, and if your curve is smooth, then you have accuracy that decays exponentially with the number of points that you've selected. And that's basically the best that any model can be. The only question is whether this method actually works, whether it introduces undue complications that are overly burdensome for numerical purposes, whether it's stable, those kinds of questions. Okay, so when we plug this summation into the governing equations, what we recover is dynamical equations for, over here, these coefficients. The coefficients to the polynomials get their own governing equations, and these coefficients, which are essentially transition rates from one compartment to the other, can be pre-computed as just related to inner products of these polynomial functions, right? And the same thing with the beta values for transmission. It's just contributions from each of these individual compartments that each have their own infectiousness, and the infectiousness of those compartments can be calculated via the inner product of this beta of tau function with the polynomial coefficient p sub n. Okay, so the cool thing is that not only does this give you the opportunity for spectral accuracy, but it also recovers this ordinary differential equation compartment type structure that was so convenient for the purposes of numerical calculations, so convenient and so efficient. Okay, so this model promises spectral accuracy, really good accuracy. Does it deliver on that promise? Or does it go unstable? Or are there any other restrictions we need to consider? So the first thing that we're going to look at is an example case. These curves that I've plotted down here for transmission and recovery are examples. You could put in literally anything that you wanted for these kinds of curves, and the model would be no more difficult to run. So this is incredibly flexible. you don't need to reparameterize a bunch of different compartments every time you want to look at a new epidemic. All you have to do is redefine what these curves are shaped like, and that's it. Okay, so for transmission, we are assigning a curve like this that says early on you're not going to transmit, but over time that rises, and then it falls again, and it has this certain skewness to it. And we're assigning a reproduction number of 2.5. So every person who contracts the disease at the beginning is likely to transmit it to 2.5 people. Okay. For recovery, we're just flipping this curve around, and we're saying early on you're not likely to recover, and then later on is when people actually start showing signs of recovery. Okay, so given this setup for the epidemic model, we'll start with the compartment model, discretization, and we set up 4 compartments and 6 compartments, and we see that the compartments, or the predictions, are all very similar to the converged calculations, but they kind of bounce around and they're not really showing signs of convergence, right? And in truth, you need a lot of compartments for these calculations to really properly converge to within a fine error tolerance. Okay, looking at the predictor corrector, we have similar errors for n equals 4 and n equals 6 compartments in the infected population, but within those similar errors at this point, we're still seeing a clear sign of convergence. So if we were to extend this analysis to n equals 8, n equals 10 compartments, these calculations would essentially look converged, and these would still be bouncing around. Okay, the other thing to note is that even if the accuracy is comparable with n equals 6 compartments at this point in time, the predictor corrector method is more efficient because it is able to take larger time steps for a specified level of accuracy, whereas the SIKR model has to take small time steps in order to have the calculations properly converge. Okay, so that's a comparison, just demonstrating that predictor corrector is indeed better than the SIKR model. But how does the Glurkin-based spectral method compare against the predictor corrector? Well, here's those predictor corrector calculations again, and here are the Glurkin calculations with m plus 1 equals 4 compartments for the infected population. And it's worth mentioning that one of those compartments is not independent of the other 3. So really, you have 3 independent compartments here for the Glurkin method, and it has already converged spot on to the fully converged results for this model. So that's pretty nice. It's showing that this Glurkin method, which we believe is new, gives you properly spectral accuracy in your calculations of an epidemic model that is parameterized in terms of time since infection and has all of the associated benefits of accuracy and flexibility and so on. Okay, so one limitation of the Glurkin method, or one potential limitation of the Glurkin method that's certainly worth mentioning, is that it gives spectral accuracy if this function, I of t and tau, is smooth. Okay? If the function is not smooth, as might happen if you have a lockdown, then this is potentially different. So if you have a lockdown, then the number of cases with low time since infection at some point is going to drop. So here there's no lockdown, cases are rising, a lockdown is instituted, and then all of the new case loads have dropped to a lower value. Okay, so if you have this break, if you have this discontinuity, then, I wanted to try and superimpose a parabola on top of this, but basically it becomes clear that a polynomial expansion is not going to provide all that great of accuracy compared to, for example, a finite difference method like the predictor corrector approximation. Okay, so that's where you can potentially get problems with Glurkin approximations, but let's see what actually happens here. So we're going to return to the same case that we had before, only at time 3, t equals 3, and that's time relative to the maximum infection period, by the way. So this should be t over capital T, less than 3, so it's been, say, 6 weeks or something like that. After 6 weeks, we're going to put in an abrupt lockdown after which the reproduction number goes from 2.5 and drops down to 1. Okay? And we're going to leave the shape of these two curves more or less intact. We're just suppressing the transmission dynamics at some time during the simulation. Okay, so what happens there? So this is once again the Glurkin calculations. This is for the same number of modes. So 4 modes total, 3 of them being independent. And we see that it basically still tracks exactly. So why is it able to track exactly even though the polynomial approximation of this infected population is known to be quite poor? Well, the reason for it is that the dynamics for transmission and recovery both involve the inner product of this infected population, I of t and tau, with a transmission rate function, beta of tau, and a recovery rate type function, phi r of tau. And when you do that, if you take the inner product of a smooth function and a non-smooth function, right, to get spectral accuracy, you only need one of the functions to be smooth, right? Because the inner product of those two is going to be the sum of the product of their coefficients attached to each polynomial, right? And if you have just one of those coefficient sets decaying exponentially, then the whole thing is going to decay exponentially, right? So you can still get spectral accuracy even if you have an abrupt lockdown put into the model, provided you still have smoothness in these other functions. Okay, but there are extreme circumstances. If you lose smoothness in one of those two functions, then the loss of smoothness in the modeling of the infected class does in fact become a problem. So here's an extreme example where we have the same thing for transmission, but we've changed the recovery dynamics. So instead of having smooth recovery dynamics, we're now saying that when a person reaches an age of infection of exactly t, that's when they recover. So this recovery curve goes from being something smooth to being a delta peak, right? So now that's not smooth. Then what we see, running the same simulation as before, so this is the same simulation, but we've just changed the recovery dynamics, and we're zooming in right at the point of the imposed lockdown. What we see is that recovered cases do this wobble immediately after the lockdown is instituted. And in the course of this wobble, we see recovered cases briefly decline, right? And that decline of recovered cases is not realistic. There's no way in the full model for someone to go from being recovered back to being infected or susceptible or something like that based on the way we've set the model up. So this is an artifact of not having enough modes included in our Glurkin expansion. So when you have something that's not smooth like this, then you would have this added burden of carrying more and more and more modes around in the model, and it would lose its advantage against something like a predictor corrector method, for example. Okay. So before I sum up and go through this listing, I do want to add that, this is actually a point to address in these bullet points here. So just a summary of the talk to this point is that we first looked at existing compartment models. We started with the SIR model, which is the the toy model that everybody starts with and that everybody knows about. It's the simplest possible model for an epidemic. And then we looked at its generalization to a multi-compartment model, the SIKR model. The pros of these kinds of models is that they're simple, they're intuitive, and they're quite fast and efficient for a coarse resolution of the disease dynamics. The cons, of course, is that they can be slow and inefficient and inflexible for fine resolution of the disease dynamics. Then after that, we covered the time since infection framework. The advantages there are that it's flexible. All you have to do is, sorry about this. Okay. Hang on. Okay, I keep clicking on my slide when I'm on my last slide here. All you have to do is define these functions of beta of tau and phi r of tau, these things that are defining how infectious a person is with increasing age of infection, how likely a person is to recover with increasing age of infection. Those are the only things that you need to define, and they're decoupled from one another, as we've said. The recovery dynamics are decoupled from the transmission dynamics, which is not typically done in most compartment model approaches. The time-since infection model approach is efficient if you use the Glurkin discretization. It is cost competitive, or perhaps even improved in terms of its cost relative to the compartment models. And a nice thing that was previously not true for time-since infection models is that it is available. It's already incorporated into the PyROS modeling software that our group was working on last year and continuing to work on, I think, even. So that was a big drawback to the time-since infection approach previously, was that if you wanted to work with a compartment model, there were existing software packages that you could use to do that. If you wanted to work with a time-since infection model, there was this perceived burden of numerical complexity that led people to believe that time-since infection models were not suitable for large, complex epidemic models that had geographic structuring and all of these other components integrated into them. But I believe that's no longer the case. If you choose the right discretization strategy, such as built into the PyROS modeling software now, you can use a time-since infection framework and be cost competitive to the compartment modeling framework. The caveat that I would raise here is that yes, it's possible to do time-since infection models at a similar cost to a compartment model, but no model is better than its worst approximation, and no model is more accurate than its supporting data. And basically, what I mean to say there is that if you don't have enough data to properly parameterize a TSI model, you're just as well using a compartment model, perhaps, in many cases. Otherwise, you're going to give yourself a false sense of security for the level of accuracy that you've put into your model. So I believe that wraps up my talk, and I will take questions if there are any.
Thank you very much, Joe. So I don't see questions in the chat, but please feel free to unmute and ask directly a question if you want to. So maybe just to start with, I have a question about so this idea of time-since infection. So the question that I have is that it seems that it's based on the fact that you know the time the people are infected, while let's say in reality or in practice, people don't know exactly precisely how or when they got infected. So how is this important to use real world data, and how is your framework sensitive to that t = 0?
Right. So I think that, so I've had some conversations about how this data could be in principle gathered. You're absolutely right that at the moment, this is not the way, the data doesn't exist in a form that would be very easily transferred to parameterize a time-since infection model. You'd have to make some level of approximations or assumptions. One of the things that does seem to be available in some data sets is case outcomes marked by the time since first symptoms, right? So when did this person first start showing symptoms? And then when did they end up going to the hospital? When did they end up being recovered? When did they end up transmitting it to someone else, for example? Okay. In terms of actual timestamps then of when someone was infected, in some cases, contact tracing may be able to give us the answer to that, right? So if somebody has COVID and they don't know it yet, and they meet with somebody in their office on this one day, right? And then they part ways, and then the first person finds out they have coronavirus, they contact the second person, that person gets tested. Now they can pinpoint the time of their infection, right? You're not gonna be able to do that for every case. But if you have a representative set of cases for which you can pinpoint the time since the actual date of infection, and then, for example, a later date at which the person started showing symptoms, right? Then you can potentially work back from those other cases where you have it parameterized by, time since first symptoms, and infer on each of those cases when a likely date of infection was. So that's what I would say in that respect.
Okay, thank you very much.
I might have one. I mean, about maths, right, and about Glurkin. So of course the epidemiology is nice, but just, I mean, the results you show for Glurkin, it does look like a bit of a miracle, and these equations do look just sort of like normal memory kernel type equations. So just because I'm ignorant, right? So if I had an equation with a memory kernel in of any kind that I just dig up from somewhere and I'm interested in it for some reason, should I just use Glurkin off the shelf right away and not think about anything else, or what should I worry about?
Is the memory kernel smooth and is it bounded?
Well, I don't have an example. I'm just asking you.
Right. So a lot of times memory kernels have exponential tails on them, for example. You wouldn't want to use Glurkin on something with an exponential tail, right?
And how would you feel about chopping the exponential tail and not worrying too much about what that bad things that's going to do? Because I guess you also have an exponential tail here, possibly. I don't know. But
the curves, I parameterized using beta distributions. So beta distributions are phenomenological.
Sure. Yeah.
But they have this property of being smooth and bounded, right?
Right, but there are definitely, in the epidemiological context, there are definitely people who spend 100 days in hospital.
Yes.
So in principle, what you've done is you've chopped your memory function, right, after 3 weeks.
That's right.
I could just do that with my physics model, I suppose. Assume
Right.
that nothing terrible will happen. But no, I see what, I mean, your point is a good one. So, okay, but smooth and bounded, then it's good.
I think so. Yeah.
Thanks, that's great.
Are there other questions?
As maybe, if I may, I have questions somewhat related to what Camille was asking, and it came to my mind that maybe it would also work conditioning not on the time of infection itself, but maybe on the time of onset of symptoms, like Camille has also suggested. So then we would probably also need some negative times, stuff that has happened before the onset of symptoms. You thought in that direction, would that make sense, or would you run into problems somewhere else?
So I think you could do that. It would just be a shift on your tau variable, right? You would have tau hat, and instead of going from 0 to t, it would go from minus t1 to t minus t1, right? Where t1 is the latency period of how long you go from being infected to experiencing symptoms.
Okay, so that might be a solution to the problem that you don't have data for time since infection, but time since onset of symptoms. If you also get a data set of the time it took until the onset of symptoms, just from studies like you have mentioned, contact tracing or whatever, then you could put these two data sets, which are at first independent, together, and then form your partitioning on the negative half and on the positive half independently.
Right. Sure. I think that ultimately that data could be processed so that those extra steps aren't necessary or aren't seen, right? But conceptually, that's what one would want to do, to take those two independent data sets and link them up in that way with the inference that one can reliably backdate a time of infection based on the date of symptoms.
I suppose you would want to infer some of these things, right? So I suppose what you really want to do is stick on some priors for the parts you don't know and form as best you can the bits that you do know. So you could use Patrick's thing to say, well, I definitely know, I know the infection curve after some time, which I'm not sure what it is since infection. So it would be a reframing of the inference problem, I suppose. But for the PDE problem, sorry, the ODE problem, it's not such a thing.
Yeah, but again, no model is more accurate than its supporting data, and no model is better than its worst approximation. So if all you know is that it's somewhere between 3 and 5 days is the average latency period, if that's the best level of resolution that you have, then it doesn't necessarily make sense to use a model that requires you to pinpoint exactly how long these different periods are. You may as well just use a compartment model that lets you fix an average, and that's all you have to fix. And then you know what the uncertainty is, and you know where the uncertainty is put in that model.
Yeah, I mean, I feel like this might be arguing the opposite way to what I usually argue, but I mean, you could have the compartment model by just putting in exponentials or gammas everywhere or something, and just, I mean, you could think of it that way, right? So just think about, if you only got one number, then you've just got to pick a distribution, and you may as well pick exponential, and that's equivalent to having a compartment model. I mean,
yeah,
this kind of argument, I think in terms of data, and if you've got a small number of parameters, how to fit them, I think it's not so different, really, the two approaches. You've got to make some approximation somewhere.
Yeah.
Okay, thank you very much, Joe, for this very interesting work on these epidemiologic models. So if there is maybe a last question, there is still a bit of time, feel free to ask it. Otherwise, we will meet for next term, so after the break. And so Patrick and I will be planning the schedule for next term. So we'll be circulating an email to collect some ideas. So that would be really helpful. And if you have suggestions, really feel free to tell us. Otherwise, thank you again very much, Joe. Thank you all for the discussion and questions, and see you soon.